Hey everyone, so I'm back and I am going to prepare a short little video here that finishes up just a few of the things we didn't get to at the tail end of chapter 2 when meeting in person. Um, so let me go over those real quick. All right, so last time we met, we talked about buffer systems, right? And we saw how systems that were capable of buffering, basically, they're capable of buffering and resisting pH change because they have, appreciable amounts of both a weak acid form and its conjugate base present at most of the time. And these can sort of act as little sponges that can sort of absorb additions of things that would normally really sharply increase or decrease the pH, right? So I wanted to talk just a little bit more about buffers. Couple of quick points about them. Are they just permanently effective? Can they just last indefinitely? You can keep adding acid and base, and it can be fairly resistant. The answer is no. And I think I showed you an example of that when we did the benzoic acid example, right? We're adding hydroxide ion to benzoic acid. Eventually, we reached a point when we did that where we ran out of benzoic acid in the system. And at that point, we saw a really sharp spike in the pH. All right? So, every buffer system is going to have what we call a buffering capacity. And so that really just refers to the buffer's ability to sort of last and be able to continuously take, sort of act as a sponge for an added acid or base before it sort of runs out and the pH sharply increases or decreases, right? Not surprisingly, the more concentrated a buffer system is, the higher the buffer capacity. Right? So, for example, you could compare two different, containers. One of them has a 0.1 molar. What do we call it? We'll just call this tris to be a little bit different. Let's say one of them has a 0.1 molar tris buffer, and the other one has a 1.0 molar tris buffer. Now, tris, both of these systems, both of these containers are going to have the same equilibrium in their system, right? They're still going to use the tris equilibrium that's in the table 2.8 on page 56 of my book. But one of them is more concentrated than the other one, right? So each of these can sort of absorb added acid or base and resist change in pH, but this one lasts longer because it's more concentrated. You don't run out of tris and tris H plus nearly as quickly as you do with the less concentrated version. So it's going to have a higher buffering capacity. Okay? So, that can change how you handle things like in the lab. If you're trying to make a buffer that you want to make sure will stand up for a long amount of time in use, probably making it a little bit more concentrated is going to be better because then it's going to be less resistant to pH change. Or not necessarily less resistant, but it will be resistant to larger additions of acid or base. All right? That's one thing. How do we pick a buffer? Right? There's so many buffers out there, right? There's two different tables of buffering systems in your book chapter, and there's oodles and oodles more of them. All right? So how do you go about picking one? Well, really, if you ever want to use a buffer, it all comes down to your target pH. That's really terrible writing there. So hold on, let me erase this. Do. All right. So you want to choose your buffer based on your target pH. In essence, you want the pKa to be close as possible to the target pH. Okay? There's a rule of thumb here as well. Generally speaking, the buffer is effective if the pKa of that buffer system is within 2 pH units of the target pH. The closer, the better. Okay? So, for example, let's say, our target pH was 7, right? We wanted to buffer for a system with a target pH of 7. All right, so what we would do is we would look at our tables and we would try to find one with a pKa as close to 7 as we could possibly get it, right? So I'm just kind of looking over here as soon as I find the page with the table. I'm looking at table 2.6 on page 46 of my book that has a bunch of these weak acid equilibria, right? So let's say, I'm looking at lactic acid, right? I'm considering lactic acid as my buffer system. Would this make a good buffer system? The answer, no, it wouldn't. Why? Because the pKa of lactic acid is 3.86, right? To be effective, the target pH needs to be plus or minus 2. So lactic acid's effective buffering range is going to be from about 1.86 to 5.86. And that just doesn't work for a pH of 7 system, right? So you keep on looking, right? If you keep on looking, eventually you get to the second phosphoric acid equilibrium. That's the one that looks like this. I did that terribly, sorry about that. There we go. All right, this one has a pKa of 7.20, which you see is very, very close to the target pH, well within the buffering range, so that would be a really good system. We'll revisit that one in just a second. It's not the only one on this list that could conceivably work, right? Well, let's see. Is it? Yeah, there's one or two others. Malonic acid has a pKa of 5.69, right? The second malonic acid equilibrium. Malic acid, the second malic acid pKa is 5.26. Each one of those is within that 2-unit range, so you could use those, but this one is the closest to the target pH, so that's why this one is the best. Okay? So, choosing your buffer, match it as close as possible to your target pH. All right. The next thing I want to briefly mention is how do you actually make a buffer, right? If you're going to be, hypothetically, if we had a lab, biochem lab, one of the things that's sort of a staple of biochem labs is making buffers, right? You frequently have to make them. So we've talked a lot about their activity, but how do you actually make them in the first place? There's a couple of different ways, all right? The first way Actually, before I get into that, I'm going to just sort of write the Henderson-Hasselbalch equation up here because this is going to be an important reference. All right, it's our magic formula that we use for so many different problems. Okay, so basically the idea is, though, if you're making a buffer system, you want to make a system that has appreciable amounts of both these guys, both the acid and the base forms. Okay? So, hypothetically, let's say, and I'm making this literally up off the top of my head, so bear with me. Let's say that we're making a formic acid buffer. All right? And I'm just going to represent this using the general formula. Formic acids, going to be a monoprotic acid, and its pKa is 3.75. All right, so usually when we make a buffer, we want it to have certain parameters, right? One parameter is, what do you want the pH of this buffer to be at the very beginning? All right, so let's just say our target pH is 4.00. Okay, so if you plug this into the Henderson-Hasselbalch equation, you could say 4.00 equals, our pKa is 3.75, plus the log of the acid form to, the base form to the acid form. All right, so what we're trying to find here is what we're really looking to do is find out what this ratio is. That's the first thing. In order to get to a pH of 4, what ratio does our base form to our acid form need to be, right? And you can algebraically manipulate this equation to do that, all right? What you would do is subtract 3.75 from both sides. When you do that, you get 0.25 equals log of A minus over HA. And then to get the actual ratio, you have to take something called the antilog. All right, it's basically the reverse of a log. How you do this on your calculator does differ from calculator to calculator. Some do it one way, some do it another way, and then even others do it maybe a third way. So what I would recommend is whatever calculator that you're using, just play around with it and even Google it. You can Google it on how to do the antilog on your particular calculator. When I use the Apple iPhone scientific calculator, literally what I do is I would punch 0.25 and then hit the button that says 10 to the X power. All right, so if you're on an iPhone, that's how you would do it. Otherwise, look up your calculator model and find out what the procedure is. But when all is said and done, and let me punch this out real quick so I can find it. One second. Comes out to be 1.78. So we know we want the base to acid ratio to be 1.78. All right. So, sort of put that in your back pocket. Remember that value. I'm going to erase this. Okay. All right, so Now we got to figure out exactly how much of which we got. All right. So there's, like I said, there's a couple of different ways you can make these. One way is to directly make your buffer solution from two different compounds. And in this case, the ones I would use would be formic acid. So literally I can have a container of formic acid, and formic acid is the acid form. It's the HA in this. And so I can directly add some HA and have a certain amount. And then you can also have the salt of your conjugate base. So if we look at formic acid, this is what formic acid looks like. When it dissociates, it gives you this. All right? The ionic form here, the deprotonated form of formic acid, that's called formate. Okay? Formate can exist as part of a salt, right? So, if you had this, right? Maybe a sodium ion associated with that negative O, that would be called sodium formate. And you can buy that. That's just something that you can buy directly from a chemical supply company. It's a white crystalline powder, sort of like table salt in a lot of ways. All right, and so, as you know from Gen Chem, if you take a sodium salt, put it in solution, it completely dissociates. So when you do this, the sodium formate will dissolve, the sodium becomes a spectator ion, and that gives you your formate, right? So if you find out the values of exactly how much acid you need, you can add that directly as formic acid. If you figure out how much formate you need, you can add it directly as sodium formate. Okay? All right, and that's how we're going to try to approach this one. We're going to try to use formic acid and sodium formate to make this particular buffer. All right. So let's